Hello and welcome to Earth Science Lecture 19, Lift and Instability. Recall that condensation occurs when sufficient water vapor is added to air, or more commonly, when the air is cooled to its dew point temperature. Condensation may produce dew, fog, or clouds. Heat near the Earth's surface is readily exchanged between the ground and the air directly above. As the ground loses heat in the evening, dew may condense on the grass, while fog may form slightly above Earth's surface. Thus, surface cooling that occurs after sunset produces some condensation. Cloud formation, however, often takes place during the warmest parts of the day, an indication that another mechanism must operate aloft that cools air sufficiently and generates clouds. This process that generates most clouds can easily be visualized. Have you ever pumped up a bicycle tire with a hand pump and noticed that the pump barrel becomes very warm? When you applied energy to compress the air, the motion of the gas molecules increased, and thus the temperature of that air rose. Conversely, if you allow air to escape from a bicycle tire, the air expands. The gas molecules move less rapidly and the air cools. You have probably felt the same effect when applying hairspray or spray deodorant. The propellant gas cools as it expands out of the nozzle. Temperature changes of this type, in which heat energy is neither added nor subtracted, are called adiabatic temperature changes. In the cases described, the change in temperature is caused by a change in pressure, not temperature. When air is compressed, it warms. When air is allowed to expand, it cools. So you're going to hear this term a lot, adiabatic or adiabatic temperature changes. Again, this is when temperature changes not because of actual temperature changes or heat changes. It's changed because of differences in pressure. To simplify the discussion of adiabatic cooling, imagine a volume of air enclosed in a thin, expandable membrane. Meteorologists call this imaginary volume of air a parcel. Typically, we consider a parcel to be a few hundred cubic meters in volume, and we assume that it acts independently of surrounding air. We can also assume that no heat is transferred into or out of this parcel. Although this model is highly idealized, over short time spans, actual parcels of air moving up or down in the atmosphere behave much in this way. Recall that atmospheric pressure decreases with height. Anytime a parcel of air moves upward, therefore, the pressure surrounding it is gradually decreasing. As a result, it expands and cools adiabatically. Unsaturated air cools at a constant rate of 10 degrees Celsius for every 1,000 meters of ascent, or 17.5 degrees Fahrenheit per 1,000 feet. Conversely, descending air comes under increasing pressure and is then compressed and heated also by 10 degrees Celsius for every 1,000 meters of descent. This rate of cooling or heating applies only to unsaturated air and is known as the dry adiabatic rate. So it's dry because the air is unsaturated, and it's adiabatic because its temperature is changing because of pressure, not actual temperature differences. So here's an example. So we have a parcel of air at 32 degrees Celsius, and it's rising. Well, as it rises, the pressure is slowly decreasing, so it's slowly expanding and slowly cooling. If an air parcel rises high enough, it will eventually cool to its dew point temperature, triggering the process of condensation. The altitude at which a parcel reaches saturation and begins to form clouds is called the condensation level. At the condensation level, an important change occurs. The latent heat that was absorbed by the water vapor when it was evaporating to release sensible heat, although the parcel will continue to cool adiabatically as it rises, the release of latent heat slows this rate of cooling down. In other words, when a parcel of air ascends above the condensation level, the rate at which it cools is reduced. The slower rate of cooling is what we call the wet adiabatic rate, also commonly referred to as the saturated adiabatic rate. Because the amount of latent heat released depends on the amount of moisture present in the rising air, the wet adiabatic rate will vary anywhere from about 5 to about 9 degrees Celsius per 1,000 meters. So here we see that again. In the dry adiabatic rate, we're rising, so we're going into lower pressure, so this pocket of air expands and cools. Eventually, it cools enough to the point at which it becomes saturated, and it reaches the condensation level. It will still rise, or can still rise, and will still cool in that process, but it cools more slowly now at the wet adiabatic rates, between 5 and 9 degrees, instead of the 10 we saw previously. So, okay, well, this is important, but what actually causes air to rise? I mean, we're talking about air rising, so what causes that? So we're going to look at a few different ways that air can rise. So why does air rise on some occasions to produce clouds, but not on others? Generally, the tendency is for air to rise or resist vertical motion. Air near the surface tends to stay near the surface, and air aloft tends to remain aloft. However, the following 4 processes can generally cause air to rise and generate clouds. The first is orographic lifting, in which air is forced to rise over a mountainous barrier. Second, frontal lifting, in which warmer, less dense air is forced over cooler, denser air. Third is convergence, a pileup of horizontal airflow that results in upward movement. And the fourth, localized convective lifting, in which unequal surface heating causes localized pockets of air to rise because of their buoyancy. So let's take a look at each of these 4 processes in a little bit more detail. Orographic lifting occurs when elevated terrain, such as a mountain range, acts as a barrier to the flow of air. As air ascends a mountain slope, adiabatic cooling often generates clouds and copious precipitation. In fact, many of the rainiest places in the world are located on windward mountain slopes. That is the side where moisture is coming off the ocean. It's the windward side. By the time air reaches the leeward side of the mountain, much of the moisture has been lost. If the air descends, it warms adiabatically, making condensation and precipitation even less likely. The result can be a rain shadow-like desert, such as the Great Basin Desert of the western United States, which lies only a few hundred kilometers from the Pacific Ocean, but is effectively cut off from the ocean's moisture by the Sierra Nevada. The Gobi Desert of Mongolia and the Patagonia Desert of Argentina are other examples of deserts that exist because they are on the leeward side of large mountainous systems. The second process we looked at is frontal lifting. If orographic lifting were the only mechanism that forced air aloft, the relatively flat central portion of North America would be an expanse of deserts rather than the area known as the nation's breadbasket. Fortunately, this is not the case. In central North America, warm air and cold air masses often collide, producing boundaries that we call fronts. Rather than mixing, the cooler, denser air acts as a barrier over which the warm and less dense air can rise. This process, called frontal lifting or frontal wedging, is illustrated in the figure on the right. In the middle latitudes, most precipitation is due to weather-producing fronts associated with storm systems that we call mid-latitude cyclones, but we'll see a lot more on that in our coming lectures. All right, the third type of lifting is convergence. When the wind pattern near Earth's surface is such that more air is entering an area than leaving, a phenomenon called convergence, lifting occurs. When air is compressed by convergence, it escapes by moving upward. One situation in which convergence causes lifting is when air is drawn into the center of a low pressure system, such as that of a low pressure system or a hurricane. The inward flow of air at the bottom of these systems is balanced by the rising cloud formation and usually by precipitation. Convergence can also occur when an obstacle slows or restricts horizontal airflow. For example, when air moves from a relatively smooth surface, such as the ocean, onto an irregular landscape, increased friction between the land and the air reduces the speed of that air. This results in a pileup of air known as convergence. The Florida Peninsula provides an excellent example of the role that convergence can play on initiating cloud development and precipitation. On warmer days, the airflow is from the ocean to the land along both sides of Florida. This leads to a pileup of air, basically above the land. And so what we see is an uplift aided by intense solar heating of the land. So as a result, Florida's peninsula experiences the greatest frequency of mid-afternoon thunderstorms in all of the United States. And last but not least was the localized convective lifting. On warm summer days, unequal heating of Earth's surface may cause some pockets of air to be warmed more than the surrounding air. For instance, a plowed field or a parking lot will absorb more radiation and hence impact more warmth than the overlying air. Let me re-say that. For instance, a plowed field or parking lot will absorb more radiation and hence impart more warmth to the overlying air than adjacent fields of crops. Consequently, the overlying parcel of air, being warmer and less dense than the surrounding air, will be lifted upward. Such rising parcels of air are called thermals. Thermals can carry birds such as hawks and eagles, and also human hang gliders to great heights. Unequal heating of Earth's surface causes pockets of air to be warmed more than the surrounding air. So the buoyant parcels of hot air, or thermals, rise, and if they reach a condensation level, clouds can form. The phenomenon that produces rising thermals is what we call local convective lifting, or convective lifting. When these warm parcels of air rise above the lifting condensation level, clouds form and occasionally produce mid-afternoon rain showers. The height of clouds produced in this fashion is somewhat limited because the buoyancy caused solely by unequal surface heating is confined to, at the most, a few kilometers of the atmosphere. Also, the accompanying rains, although occasionally heavy, are of short duration and widely scattered. So now we can kind of combine what we've discussed into the topic of atmospheric stability. So this is leading to the concept of cloud formation that we'll look at in our next lecture. So, when air rises, it cools and usually produces clouds. So why do clouds vary so much in size? And why does the resulting precipitation vary so much? Well, these are answers that are closely related to what we call the stability of air. Recall that an air parcel can be thought of as having a thin, flexible cover that allows it to expand, but prevents it from mixing with the surrounding air, such as a hot air balloon. Imagine that you find such a parcel with some given starting temperature and forcibly lift it to a higher location. Its temperature will decrease because of expansion. Its final temperature will depend on how warm it was to begin with and how high up you have lifted it. When you let go of this parcel of air, what happens? Well, if it is cooler and more dense than the surrounding air, it will sink back down. Air of this type is considered stable, and it resists upward motion. But if that parcel of air is warmer and less dense than the surrounding air, it will continue to rise. Specifically, it will rise until it reaches an altitude where its temperature equals that of the surroundings. This type of air is considered unstable. If air is warmer, and therefore less dense than the surroundings, it rises. Hot air balloons rise through the atmosphere exactly for this reason. They are hotter and less dense than the air around them, and so they rise. Stability is a property of air that describes whether it resists rising or may rise spontaneously in an unstable case. To determine the stability of a given parcel of air, we first need to know how the temperature of the atmosphere above a parcel changes with height. This measure, determined from observations made by radio sounds and aircrafts, is called the environmental lapse rate. It is important not to confuse this with adiabatic temperature changes, which are changes in the temperature of a rising or sinking parcel of air caused by expansion or compression. When an unsaturated parcel of air is forced to rise, it expands and cools at the dry adiabatic rate of 10 degrees Celsius per 1,000 meters. In this example, the temperature of the rising parcel of air is lower than that of the surrounding environment. Therefore, the parcel is heavier than the surrounding air, and if allowed to do so, it will sink back to its original location. Air of this type is considered stable. So again, take a look at the image on the right. We have rising air, but notice that at all points along its rise, its temperature is lower than its surroundings. 15 versus 5, 20 versus 15, it's always cooler. And so this has a tendency to sink back down because it's colder and more dense. So this is stable air. To illustrate, I'm going to go over this in more detail. We examine a situation in which the environmental lapse rate is 5 degrees Celsius per 1,000 meters. In other words, for every 1,000 meters we increase in height, we are cooling by 5 degrees. That is the environmental lapse rate. Under this condition, when air at the surface has a temperature of 25 degrees Celsius, the air at 1,000 meters will be 5 degrees cooler, or 20 degrees Celsius, and so on. So at first glance, it appears that the air at the surface is less dense than the air at 1,000 meters because it is 5 degrees warmer. However, if the air near the surface were unsaturated and were to rise to 1,000 meters, it would expand and cool at the dry adiabatic rate of 10 degrees Celsius per 1,000 meters. Therefore, upon reaching 1,000 meters in height, its temperature would have dropped by 10 degrees Celsius. Being 5 degrees cooler than its environment, it would be denser and then tend to sink to its original position. Hence, we say that air near the surface is potentially cooler than the air aloft, and therefore will not see air rise on its own. So again, the air just described is stable and resists vertical motion. Stated quantitatively, absolute stability prevails when the environmental lapse rate is less than the wet adiabatic rate. So this is a mouthful, and this is very hard to grasp because of this intense verbiage. So this is just saying that the temperature of the rising air happens to be less than that of the environment. So like the situation we saw previously, our rising air is always cooler than our actual temperatures. So we call this absolute stability. Even if this stable air were to be forced above the condensation level, it would remain cooler and denser than its environment, and thus it would tend to return to the surface. The most stable conditions occur when the temperature in a layer of air actually increases with altitude rather than decreases. When such a reversal occurs, a temperature inversion is said to exist. Temperature inversions frequently occur on clear nights as a result of radiation cooling of the Earth's surface. Under these conditions, an inversion is created because the ground and the air immediately above will cool more rapidly than the air aloft. When warm air overlies cooler air, it acts as a lid and prevents appreciable mixing of the air. Because of this, temperature inversions are responsible for trapping pollutants in a narrow zone near Earth's surface. So here is an image, albeit an involved one, that signifies absolute stability. Absolute stability prevails when the environmental lapse rate is less than the wet adiabatic rate. So here we see that the environmental lapse rate is 5 degrees, meaning for every 1,000 meters we decrease by 5 degrees. Our rising air, however, is decreasing at the dry adiabatic rate here of 10 degrees Celsius. So even though we start at the same temperature at the surface, the rising air is cooler than its environment at all stages. And so we have a tendency to see this air sink back down. And so we don't get towering thunderstorms with these. We might get some clouds to form if it gets pushed up far enough, but overall we don't see anything too dramatic. So now let's talk about the opposite scenario. At the other extreme from absolute stability, air is said to exhibit absolute instability, when the environmental lapse rate is greater than the dry adiabatic rate. In other words, when the temperature of the rising air is greater than that of its environment. So, as we'll see in the figure on the next slide, the ascending parcel of air is always warmer than its environment, and thus it will continue to rise because of its own buoyancy. However, the conditions needed to render the air absolutely unstable mainly occur near Earth's surface. On hot, sunny days, the air above some surfaces, such as shopping center parking lots, is heated more than the air over adjacent surfaces. These invisible pockets of more intensely heated air, being less dense than that aloft, will rise like hot air balloons. This phenomenon produces the small, fluffy clouds that we associate with fair weather. Occasionally, when the surface air is considerably warmer than the air aloft, clouds with considerable vertical development can form. So here's an example of this, absolute instability. So now, let's say our temperature decrease is about 12 degrees for every 1,000 meters. Well, we're still only cooling off at the dry adiabatic rate of 10. So for every time we step up 1,000 meters, the actual air temperature is cooler than we see our temperature of the rising air. So 28 in the environment, but 30 here. So it's still warmer, which means it's going to still rise. And so we get lots of vertical development as a result of this. A more common type of atmospheric instability is called conditional instability. This occurs when moist air has an environmental lapse rate between the dry and wet adiabatic rates, that is, between 5 and 10 degrees per 1,000 meters. Simply, the atmosphere is said to be conditionally unstable when it is stable for unsaturated air, but unstable for a saturated parcel of air. Notice, when we look at the following figure, that the rising parcel of air is cooler than the surrounding air for nearly 3,000 meters. With the addition of latent heat, in fact, let's just go to it now. So let's look at this here. So I'll start this statement over. So notice in the figure that the rising parcel of air is cooler than the surrounding air for nearly 3,000 meters. So here we are. The rising air is at 40, 30, and 20, but the air around it is 40, 31, and 22. So it's warmer in the environment than it is for the rising part of the air. With the addition of latent heat above the condensation level, the parcel of air becomes warmer than the surrounding air. From this point, along its ascent, the parcel will continue to rise because of its own buoyancy. That is, without the aid of outside lifting. Thus, conditional instability depends on whether the rising air is saturated. The word conditional is used because the air must be forced upward, such as over the mountainous terrain of, say, the western United States, or over a cold front like we see in this image, before it can become unstable and then begin to rise on its own. So air will tend to sink for a while, but if it happens to be forced over something so that it pushes it up into an unstable environment, then the clouds can form themselves. So let me go back to this actually. So in summary, the stability of air is determined by measuring the temperature of the atmosphere at various heights. A column of air is deemed unstable when the air near the bottom of the cloud is significantly warmer and less dense than the air aloft, indicating a steep environmental lapse rate. Under these conditions, the air actually turns over as the warm air below rises and displaces the cold air aloft. Conversely, the air column is considered to be stable when the temperature drops relatively slowly with increasing altitude. The most stable conditions occur during a temperature inversion, when the temperature actually increases with height under these conditions and there is very little vertical air movement. So this leaves us with the discussion of why this matters. From the previous discussion, we can conclude that stable air resists upward motion, whereas unstable air ascends freely because of its own buoyancy. But how do these manifest themselves in our daily weather? Because stable air resists upward movement, we might conclude that clouds will not form when stable conditions prevail in the atmosphere. Although this seems reasonable, recall that processes exist that can force the air to move upward. These processes, again, include orographic lifting, frontal wedging, and convergence. When stable air is forced aloft, the clouds that form are widespread and have little vertical thickness when compared to their horizontal dimensions, and precipitation, if any, is relatively moderate. By contrast, however, clouds associated with the lifting of unstable air are towering in often great thunderstorms and occasionally even tornadoes. For this reason, we can conclude that on a dreary, overcast day with light drizzle, stable air has often been forced aloft. On the other hand, during a day when cauliflower-shaped clouds appear to be growing as if bubbles of hot air are surging upward, we can be fairly certain that the ascending air is unstable. So again, in summary, stability plays an important role in determining our daily weather. To a large degree, stability determines the type of clouds that develop and whether precipitation will come as gentle showers or heavy downpours. So the focus of our next lecture will be on the cloud types that we find because of this. But before we get there, let's go through a few questions. The dry adiabatic rate of change for an unsaturated parcel of air is what per 1,000 meters? Okay, in this case, the answer is B. The rate of cooling is 10 degrees Celsius per 1,000 meters in the atmosphere. Again, this only applies to unsaturated air. When elevated terrain, such as a mountain range, acts as a barrier to the flow of air, what occurs? Okay, in this case, it's orographic lifting. And if you actually remember, way back into our discussion of mountain building, the process of building a mountain is called orogenesis. So the names have some correlation here. So with orographic lifting, air is forced to rise over mountainous barriers. And last but not least, we have question 3. When the environmental lapse rate is less than the wet adiabatic rate, what prevails? So this one can be tricky. Remember, environmental lapse rate is the temperature of the environment. The wet adiabatic rate is the temperature change of the actual parcel of air. So in this case, the environmental lapse rate is less, meaning it's going to be warmer in the air around the region in which air is rising, and so it doesn't rise on its own. So we have stability in this case. All right, as always, thanks for watching and have a great day.